Hi everyone, how are you all? Hello, Viraj Patel. Hello, Devesh. Hi, Kavya. Hello, Sonam. Hi, Pankaj. Good morning. Good morning, everyone. Hi, Prankush. Hi, Abhinav. Hi, Partha. So, let's get started. So, today we are going to start a new topic, which is linear transformation, right? So, let's start. Now, these topics like linear transformation, change of basis, these topics are actually important to understand many fundamentals in machine learning also. So that's why I want to cover all of these topics so that you don't get any difficulty in machine learning, right? I mean, any difficulty in understanding the concepts of machine learning. So now, let's just start with the today's topic, which is linear transformation. So, you people might have heard about the function. So, how many of you have heard about the function? For example, that I can say that x square is a function. How many of you know about the basics of function? It means that I can say that it takes it takes some values from, let's suppose it is a function f, okay, which takes some value from r, and then it maps to, let's suppose, some value from r, right? So it means it is a function which takes a real number probably, and it give you the real number. For example, if I just ask you what is 2 square, then you will say it is 4. What is minus 3 square, then you will say it is 9 or something like that, right? Like, I mean, this is a function which takes a value from real number and finally gets to the real number. So for example, it takes this real number and finally give you this real number, which is 4. It takes this real number, finally give you this real number, which is 9. So this is a function. Now today we want to have some functions over the vector. So currently it seems like it is from R to R, but today we want to have function from, for example, maybe R2 to R3 or something like that, right? So that's the only difference. So what we are going to do, we are going to take some space, some vector space, and then we are going to say, let's just define a function from this vector space to another vector space, okay? Or maybe the same vector space, doesn't really matter. So for example, let's suppose this is V, and let's suppose this is another vector space, which is W. Then I will say there's a function which is mapping this the vectors from this to this, right? So these kind of functions I want to talk about today, and that too with some special structure. So these kind of functions which are mapping from one vector space to another vector space, this is the one thing. And not just any random functions. I want to talk about something called as linear functions. Okay, let's just see that what are those linear functions. So one of the property of those linear function is that, or maybe you can say linear map. Okay, linear map or linear function or linear transformation, whatever you want like to call. So one of the property for the linear transformation or for the linear map is that if you have zero vector, okay, in some vector space, then after the transformation it remains the zero. Okay, so which means the origin doesn't get shifted. This is one of the property. Another property is that let's suppose that you are having, let's suppose, one vector, okay, let's suppose u, and or maybe some vector, let's suppose 1 2 3, and then let's suppose you multiply some number to this, let's suppose you multiply 5. Then what you will be getting? You will be getting 10, sorry, 5, 10, and 15, right? This much you will be getting. If you multiply a vector with, let's suppose, some scalar, this much you will be getting, right? These two are equal. Now if I want to talk about the linear function or the linear map, they say that the structure is linear, which means that if you multiply and then if you multiply a scalar with a vector, then you get this, right? So the linear function says that or the linear map says that if you take the transformation here, which means if you take the transformation of this, it is same as basically, this is same as, let me just write it. So don't worry. Currently, it might not be 100% clear, but in just few minutes it will be clear. Okay, in just few minutes. So what I'm trying to say is that, let's suppose you take a function of this particular vector. Okay, function of this particular vector. Then either you take a function of this particular vector, or maybe you can multiply a 5 later on also, which means first you take the transformation and then you multiply later on. If this property is satisfied, then along with one more property I will tell you, then we call it linear transformation. Okay, so don't worry, it will be clear in just few minutes. Let me just give you one more property. Let's suppose you have two vectors. Okay, let's suppose you have two vectors. Maybe one is 1 2 3, another one is, let's suppose, anything. Okay, maybe 4 5 6, and then you take the transformation. After addition you take the transformation, or you take the transformation separately and then you add them later on. For example for example something like this. If these properties are satisfied, then we call it linear function or linear transformation or linear map, whatever you like to call, right? So for example, which means which means either take the transformation after the addition, or you first take the transformation and then you add. Okay, if these crucial properties, so basically, actually, in short, there are only two properties, which is this one and another property is this one. If these two crucial properties are satisfied by any function from any vector space V to any vector space W, then we call that function as a linear function or the linear map or the linear transformation. Okay, so these are the two crucial properties that has to be satisfied. So this one and this one.
Hello, sir.
Yeah, please tell me.
Sir, then using these two properties, then I can say that transformation of a linear combination of vectors is basically the linear combination of the transformations.
Yeah, I will summarize both of these properties. So you are talking in terms of the combination, right? Combination of these two
Yes, sir.
properties.
Yes, yes.
Yeah, so I will come to that point. Okay. Okay. So basically, these are just mathematical notation. Now I will tell you a little geometrically that how these properties are making sense, and how you can make use of this linear transformation. Okay. So first, let me tell you with one visualization that I found at Three Blue One Brown. So there is one YouTube channel, you might know about it. This is through Three Blue One Brown. This is quite popular channel. As you can see, this particular video has got, say, 4.7 million views. Okay, so they are actually very popular for their visual representations. So let me just go through. Yeah, they're one of the representation that I liked. So you see this. Let's suppose these are this is your normal vector space. Let's suppose this is R2. Okay, and then if you, let's suppose you have multiple vectors here. Maybe, okay, for example, just try to understand why this. Maybe let me go to the representation that they were having. Yeah. So let's suppose this is your usual R2 vector space. Okay. This is your usual R2 vector space. And then you do some linear transformation. Then what it will do, it will make this R2 vector space. Most of the vectors might look something like this. So basically, it was your R2 vector space. Now, after the linear transformation, your vectors may get stretched, or your vectors may get rotated. Okay, so this kind of grid you will be getting after linear transformation. This was the original grid, but this kind of grid you will be getting after linear transformation, which means your x-axis, your y-axis, your x-axis, y-axis may get rotated, may get stretched, may get shrink, or something like this. But they have given you the examples which are not linear transformation. For example, this is linear transformation. From here, let's suppose from here, if you go to something like this is linear transformation. Okay, if you are just stretching, or if you're rotating. but they will tell you what are not linear transformation. This is linear transformation if you are just stretching the grid, okay, or the rotating the grid. Now, there will be the examples which are not linear transformation, which are next to yeah. So these kind of examples are not linear transformation. I mean, if you are not following those property. I mean, this is just a visual representation that if you are doing something random, which is no, it is not linear transformation. These kind of things are not linear transformation. Okay, we will see mathematically also, but I will like I just want to emphasize geometrically. Okay, so basically here these kind of transformation are not linear transformation, right? Now let's just try to understand first mathematically, then we may switch back to this particular visual representation. So what do I mean to say is that you have some vector. Let's suppose you have some vector u, and then you multiply this vector by c, right? Then you take the transformation of this cu. It is same as you first take the transformation and then you multiply. Okay, so basically this is called, we want to preserve some structure. Okay, that structure is linear. Either you multiply first and then you take the transformation, or you first take the transformation and then you multiply. Okay, this is the first property. And the second property is that, as I told you, if there are two vectors, you first add them and then you get you take the transformation, or you take the transformations individually and then you add them later on. Okay, so if these two properties are satisfied, then we call it linear transformation. Okay, if this kind of transformation is there, then we call it linear transformation. Now you tell me, okay, now you tell me just by looking at these two properties, that what about the zero vector in the linear transformation? What happens to zero vector? Okay, if I just ask you, what if u is zero? If u is zero, then don't you think that c of t of you take any scalar c into zero, should be actually, it should also be satisfied like this, right? It should also be satisfied like this. So it is t of zero equal to c into t of zero, right? So what do you infer from this? I mean, some number maybe x equal to cx. What do you infer from this? What is the value of t of zero? From here, can you tell me what is the value of t of zero? Can anyone tell me? See, see, what I'm telling you is that t of zero equal to c into t of zero, isn't it? You can take c into t of zero minus t of zero. I mean, you can take this t of zero on left or right, and then maybe you will be getting t of zero c minus 1 equal to 0, right? I mean, this is just one thing I'm telling you. Either if let's suppose c is some c minus 1 is okay. For example, let's suppose some non-zero. Okay, I mean, if c equal to, even if c equal to 1, it won't matter. But for example, for this sake of understanding, suppose c is not 1, then from here you will be getting t0 equal to 0, right? So what I'm trying to say here is that if these two properties are followed, okay, then origin doesn't get changed. I mean, automatically it is the byproduct. Okay, you don't have to do anything. It is just a byproduct that origin doesn't get changed, which means if this is a linear transformation, then the origin will stay. Okay, and also as I told you that either you first take the transformation, or I mean, then later on multiply, or you first multiply and then take the transformation. So both are the same thing. For example, see here, let me just play through this video quickly. Here they are telling this, these are the not linear. Some are getting curvy. So if the line are getting curvy, or maybe the origin is moving, like for example, if this was the origin and then ultimately let's suppose the origin is moving, then also it is not a linear transformation, right? I mean, that's what mathematically also we know. Or something like this, then okay, you will get to know this was also not actually linear transformation. If something is getting curved, then it is also not linear transformation. Okay, it is just a geometric representation. We will see the mathematical examples also. Okay, if the grids are evenly spaced and the and just parallel, then it is a linear transformation. If it is getting rotated or something like this, these all are linear transformation. Okay, these all are linear transformation. Okay, so yeah, so you see this, that this is, let's suppose you take, maybe you take two vectors. Okay, what vectors they have taken. Okay, let's suppose you have taken just one vector, two vector, doesn't really matter. So suppose these are the two vectors you have. Okay, these are the two vectors, for example. And then, if you add them, okay, if you add them with some number, okay, if you add them with, let's suppose -1 of something and 2 into this, okay, -1 of this and 2 into this, then either you do this addition in the transform space, which means after the transformation you do this addition, or you first do the addition and then you later on transform. It won't matter. Okay, so maybe see here. Just a second. Yeah, I think here they want to emphasize something. So let's suppose these are the, these are the two vectors which I want to, let's suppose these are the two vectors which I want to multiply this vector 1 with -1, this first vector with -1, second vector with 2, and then add them. Okay, then you do that kind of calculation in the transform space, or you first do, okay, for example, you do in this space, and then you probably, let's suppose you are getting this vector, and then you later on transform. It doesn't really matter. So it is the same thing that I'm talking about here, that either you first add and then transform, or you maybe do, you can do all of this, I mean in the transform space, in the sense, you take the transformation of this, take the transformation of this, and then you can add. So the addition can happen before the transformation or after the transformation. Okay, so maybe after some mathematical examples it will be more clear. So let me just go through the mathematical examples. Okay, like for example this, let's just check whether this is a linear transformation or not. So what it is doing, okay, so the question here is that check whether it is a linear transformation or not. So how to check, by the way, can you tell me? We need to check if the two properties that I mentioned are satisfied or not. Okay, so question is that check if given is linear transformation. Okay. So what you will do, you will look at it and then you will check the true properties. What are those two properties? Let me just, write those two properties again. So it is that you multiply by the scalar later or now, or you add the vector, like this, or maybe in the transform space. Okay. So let's just see if these two properties are satisfied or not. Now, what you will do, you will check. Let's suppose you take any, any two vectors. So let's suppose you take from R3, right? Let's suppose V is V1, V2, V3. W is W1, W2, W3. Can you tell me what is T of V? What is T of V? Based on this, it is just saying that, okay, sorry, it is from R3 to R3 only. Sorry for the typo. So it is saying that you take XYZ and then you do XY0. So which means what is T of V? It will be V1, V2, and then 0. Is this okay to everyone? Is this T of V okay? If I'm taking V is like this, then is this T of V okay to everyone? I hope that's fine, right? Okay. Okay. Now let's just check if everything is good, which means the properties are satisfied or not. Okay. Cool. So this is T of V. Can anyone tell me what is T of W? T of W you can write similarly, right? What is T of W? It will be W1, W2, W3. Sorry, W1, W2 and 0, right? Okay. Now you tell me, if you first take the addition and then you take the transformation, what it will be? It will be just V1 plus W1, V2 plus W2 and 0. Or you first take the transformation, I mean you do this and then you add. Will it really matter? Tell me. No, right? See, let me just tell you what I mean to say. That if you know, let me write it here. So if you do something like this, T of V plus W, right? It will be V plus W is V1 plus V2 plus, I mean V1 plus W1, V2 plus W2, and then V3 plus W3, but you are taking T of this, then it will be just 0, right? Okay. Or you first take T of V and T of W and then you add them. So what is the addition of T of V and T of W? Will it be same or different? Tell me. V1 plus W1, V2 plus W2, and then 0. It will be same, right? It will be same. So since this is same, so this property is actually getting satisfied. What about this property? You can easily check that this property is also being satisfied, right? I mean, you multiply here or you first multiply, doesn't really matter. Ultimately, you have to drop or you have to make the 0 last coordinate at the 0, right? So it won't really matter. Okay. So it seems like that this particular transformation is a linear transformation, right? Okay. So I can say this is a linear transformation. Let's just quickly check whether these transformation, okay, are linear or not. In each case, determine whether T is linear. Briefly justify. So let's just check. So the first thing, okay, x1 minus x2, x1 plus x2 and 1. Do you want to check it? So basically, it is taking x1, x2, and it is giving you x1 minus x2 plus x2 and then 1. Okay. See, if you take any vectors, okay, if you take any two vector, maybe let's just take any two vector. Okay, can anyone guess whether it will be linear or not? I mean, just a random guess. Okay, just at looking at it, just a random guess. Okay, don't satisfy the property. Just a random. Okay, just a random guess. Okay, so some of you are saying no, and just one or two are saying linear. Okay, so most of you are saying this is not a linear transformation. Okay, actually it is not a linear transformation. You might have guessed it because of this constant one. Okay, if the constants are involved, then it is not a linear transformation. Let me tell you why. See, if you for any vector, okay, for any vector summation, u plus v, whatever you do, okay, ultimately for any vector, okay, this is ultimately just one vector, two vector. Tell me, this is just one vector, two vectors. This particular vector, this is just one vector, right? I mean, u plus v is just a one vector. U v individually might be two vectors, but after the addition, it is just a one vector, right? So for any one vector, it is giving ultimately at edge one. So basically, I mean, I let's suppose I do not even care about what is this value, what is this value, but ultimately this is one, right? But if you take them individually, if you take them individually, then don't you think that here also you will be getting ultimately one? Okay, whatever this is, here also ultimately one. But individually, if you add them, don't you think it will be two here? But if you do the linear transformation, it will be one here. You getting my point? What I'm trying to say? So here, see, uh, for any vector, ultimately after the linear transformation, it is saying one. Oh, sorry, after the transformation, it need not to be linear. So after the transformation, they are saying it is one, right? So after u plus v, it will be one. For u also it is 1. For v also it is 1, right? After the addition, it will be 2, isn't it? After the addition, it will be 2. But here, I'm just looking for ultimately if these two has to be same, then I'm just looking for 1. So you can't get 1 after the addition, right? After the addition, anyway, you will be getting 2. So that is why this is not a linear transformation. Is this okay to everyone? Okay, let me know. Okay. So now let's just check B. Okay, let's just check B. For B, let's just probably take some, values. Maybe I can just take a counter example using some values. Maybe let's just take a vector x, y. I want to take x something like that, which already have the power of 3. Maybe 2 power 3 I can take ultimately because I need 1 by 3. Maybe I can take 8, right? And y could be anything. Let's suppose 2 or 3 or anything. Okay. And you can take anything. Okay. Let's suppose 5. Or maybe let's take one more vector where x is something like this. Maybe 3 power 3 is what? How much 3 power 3? Can anyone tell me? 27, right? So let's just take something like this. Okay. I mean, let's just take two vectors u and v. Okay. So just tell me, if you take the transformation of u, what it will give you? If you take the transformation of v, what it will give you? Here, can anyone tell me quickly? Transformation of u. I think y coordinate they are having like this, and x coordinate will be 2, right? And here it will be 4 and 3, right? Okay. So after the after the transformation, you are getting like this. If you add them, after the addition, you will be getting 9 and 6. If you add them, you will be getting 9 and 6. Okay. Do you think if you first add them, this will be leading to the 6 ultimately? Sorry, 9 and 5. Okay. This is 9 and 5. Okay. If you first add them, which means 8 and 27, then it will be whatever it will be. Is it 5? I mean, ultimately it has to lead to 5 because the coordinates are reversing. I mean, if you add them, then you take the transformation. Is it 9 and 5? No, right? So that's why it is not a linear transformation. I mean, there are multiple ways to check it. Maybe you can just check with the multiplication of something. Let's suppose you take the transformation, or maybe just with just one vector. Maybe you can just check. You take the transformation and then you multiply by the scalar, right? For example, if you just want to check with one vector, you take the transformation and you multiply by the scalar. If you multiply by the scalar, let's suppose some scalar, multiply by scalar, let's suppose 3, okay, or maybe 4 or whatever, right? Maybe 4. What you will be getting? 20 and 8. You will be getting 20 and 8. So this is 4 into t of u. 4 into t of u is 20 and 8. Do you think if you multiply by the 4 first, okay, then it will be okay, it will be, if you multiply by 4 first, then it will be 32 4u, 32 and 20. And now you take transformation of 32 and 20. Will you be getting from here will you be getting 8? No, it is not a 8 cube, right? It is not a 8 cube. If it is 8 cube, then you will be getting 8. But if it is not 8 cube, you won't be getting 8, right? So you can just check with one vector or maybe just two vectors. Okay, don't worry, the checking is not that hard as it might seem for now. It will be very intuitive in just few examples. Okay, I will tell you one very short trick. Okay, but easy and short trick. But for now, let's just do a long method, which is looking like this. Okay, so by the way, is this okay to everyone that these two, I mean, A and B are not linear transformation? Okay, A and B are not linear transformation. Let's just check if the third one is a linear transformation or not. What do you think? I mean, intuitively, do you think it is a linear transformation? It is, I think, R3 to R1, right? R3 to R. This is something which is changing R3. to R. Maybe you can multiply and then you can take multiplication common later on. I think multiplication will satisfy. You can add. Okay, so I think this is a linear transformation. Okay, let's just check. Let's just check quickly. Let's take maybe 1, 2, 3. Okay, maybe 4, 5, 6. If you add them, you will be getting 5, 7, 9. Right? If you add them, you will be getting 5, 7, 9. Then transformation of this is what? Transformation of this is what? 10 minus 5 into 9, which is 45, which is minus 35. Right? If you take transformation of this, then it will be 2 minus 15, which is minus 13. If you take transformation of this, it is 8 minus 30, which is minus 22. Now, if you add them later on, are you getting 35 minus 35? Yes, right. I mean, it is not a way to prove. Okay, just using an example, I cannot prove it, but I'm just giving you the intuition that okay, if it is most probably it should be satisfied in all the examples. Okay, I'm just taking instead of taking V1, V2, V3, I'm just taking with 1, 2, 3 or something like that, right? So it is a linear transformation. So now let's just do one more question, and then we will see one very nice and short trick that how to identify whether it is a linear transformation or it is not a linear transformation. Okay, let's just see. So it is a linear transformation, right? And these are not the linear transformation. Okay. Now let's just see this question also. So what they're saying, which of the following transformation are linear? Just tell me, is this one a linear? What do you think? Intuitively, what do you think? See here, after the transformation, you should always get the positive number. You should always get the positive number, right? I mean, the transform vector should always be positive. But if you first take the transformation, or maybe you can multiply by the negative number, won't you think that it will be a problematic situation or something like this? So just try to see that which one is linear. You see, intuitively you might understand this in multiplication. These things are never linear. Okay, I will tell you one very nice and short trick. But for now, you can just see that okay, intuitively this multiplication is not a linear. This mod function is also not a linear. Why? Because ultimately, just like this, see, just like this, here we have argued that ultimately we want 1, right? After the transformation, we want 1. The transform vector should have 1. Now here, if you talk like this, then the transform vector should always be positive. But let's suppose there is 2, 3, right? You take the transformation first, and then you multiply by minus 3. What it will be? 2, 3 will be, I think, just 2, 3, and then it will be minus 6 and minus 9, right? So if you multiply the scalar later on, you will get a minus 6 and minus 9. But if you multiply the scalar first, then it is 6 and minus 9, right? 6 and minus 9. So it is obvious that this is not a linear transformation. Is this okay to everyone? Okay. So maybe I can just remove this so that later on I can have the question and the answer on the different slide. This is the question. This is the solution of this. Okay. Okay. So now, sorry. Now let's just see about this B, C, and D, whether these are linear transformation or not. What about B? See, if it is a linear function or something, then it is always a linear transformation. Okay. I mean, you can check it, but if it is a linear function, then it is a linear transformation. But the linear function should not contain the constant. Okay. It will be a problem. If it is containing a constant, it is not a linear transformation. Okay. Not a linear transformation. Can anyone guess why? Yeah. So basically, what happens that if you add them, okay, after the transformation, if you adding, it will be ultimately addition of two, right? Plus one plus one. But like after, see, you first take the transformation, let's suppose you first take the transformation, and then you add, right? Then you add, it will be ultimately you are adding two, right? Ultimately you are adding two. But the transformation says that you if you first take, if you first add them, and then you take the transformation, then you will end up adding one. Okay. So basically, let me just tell you the final, the trick that I'm talking again and again. So see, the trick is, it is written here in the remark section. Let's just see. And also you can see, you do you remember for the linear transformation? For the linear transformation, the constant, sorry, the zero vector always remains zero, right? If you put zero here, then also you can quickly check. If you put zero here, do you think do you think that zero is mapping to zero only? Do you think? No, right? So basically, it should not be shifted. Okay, I mean the origin should always be there. So if the origin is shifting, then it is not a linear transformation. I mean, it is just a quick check. Okay, just a quick check. I mean, let me just also talk about the short trick that I'm again and again saying to you. Using this short trick, you can quickly identify whether something is a linear transformation or not. So this is a short trick. T is linear if and only if each entry of the output is linear function of entries of the input. Okay, with no constant terms. So this is very very important and very nice remark, or very nice short trick, which we can remember is that if the output is a linear function of the input entries, and there should no constant term, then it is a linear function. So tell me directly in this particular question, is the output is a linear function? See, this mod is not a linear function. I mean, a linear function in the sense it should be either C of, I mean, if the entries are, let's suppose, x1 x2, then it should be C of x1, c1 x1, c2 x2, like this. Okay, like this. So here, this is not a linear function. This is a linear function. This is a linear function, but it is a constant. So no, it is not a linear function. So only B is the answer here. Okay. So very quickly you can identify that which of the following are linear transformation. It is a potential gate question, I can say. Okay, it is a potential gate DA question. They can definitely ask this. I mean, in maybe next year, next to next year. I mean, somewhere they can ask. Okay, I'm not sure, but yeah, it is a potential gate question, because in gate they will not ask you very 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 tough question. They just want to make sure that you understand so much that you can, you're eligible to understand the MTech curriculum. So basically, the gate DA is not expected you to make a mathematician, or expected you to make a machine learning scientist or something. They are expecting you to understand their MTech curriculum. So which means that if they're starting something in MTech, okay, I mean, if they're starting some course in MTech, then they do not want themselves to teach these basics. Okay, they want that, okay, you understand these basics, so that their work is easy. They want they want us, which means me and you guys, to do that hard work, so that their work become easy and they can have a kick start, which means they can directly work on the problems, or they can directly work on the algorithms which are important to machine learning, and which are significant. So which means that the expectation is not that they want you to be machine learning scientist, or the mathematician. The expectation is just that they want you to understand their MTech curriculum. Okay, I mean, since this is MTech entrance examination, so this is their expectation. Okay, I mean, maybe it may increase later on, in the sense that after 10 years, it might so happen that the curriculum, the machine learning is so basic that it is in the BTech, first year, second year. Then at that point in time, the MTech level will get increased. If MTech level is getting increased, then obviously the gate level will get increased, which means, I mean, what I mean to say here is that, see, currently, let's suppose, see, earlier, I can say, earlier, maybe you can say, before 2020, before 2020, let's suppose there was, I mean, I'm just assuming, let's suppose there was no ML courses in BTech. Okay, let's suppose there was no ML courses in BTech, and there were only ML courses. Only good ML courses are in MTech. At that point in time, there was no gate, right? I mean, no gate DA. So basically, since they're starting the ML courses in MTech itself, so they used to teach all of this. Okay, they used to teach linear transformation, change of basis. They used to teach all of this in MTech directly. Okay, so all of this which we are studying, they used to teach in earlier in the MTech itself. Now the MTech level has been increased because the field is changing, right? Now the MTech level is increased. So now in MTech, they have more stuff to teach, much more stuff to teach actually. For example, now you have large language models, right? Which is Chat GPT. It comes under large language model, LLM. So there are multiple things, language models, in the computer vision also, the fields are changing, in the natural language processing, in the machine learning, in the deep learning, things are rapidly increasing. So in the MTech they have much more stuff to teach now, to be honest. Okay, so since they have much more stuff to teach, they do not have time to teach these basics which we are currently going through. So that is why the basics they have shifted in BTech. So they have shifted the basics here, or not shifted. I can say they are slowly shifting, slowly shifting basics before MTech. They doesn't care if that is in BTech or not, but they just want to make sure that if you're coming to MTech, then they do not have to teach all of these basics. Okay, so either you do it in the BTech or you do it during the gate preparation. They doesn't really care. So, but they are shifting before MTech basically. Okay, that's their agenda. So basically, all of these basics that we are currently studying, they're trying to shift the basics here. Okay, obviously they have not shifted all of this. Okay, I mean all of the basics or all of the fundamental things here, but slowly they are shifting. Few things they have shifted this year, and maybe in the next 5 years they will be shifting more and more here. Because see, it is like that कि यहाँ पे जैसे ही लोड बढ़ता जाएगा, जैसे ही फील्ड फील्ड इवॉल्व होती जाएगी, यहाँ पे एमटेक में उनको जितनी ज्यादा कॉम्प्लेक्स चीजें पढ़ानी होंगी, उतनी ही बेसिक्स और उतनी ही चीजें वो यहाँ पे डालते जाएंगे कि आप पहले से सीख के आओ, right? So I hope you are getting my point. So it is just because they have much more stuff to teach, right? See, when I did my MTech, there was no concept of large language model. Have you heard about BERT? There is something called BERT model. Anyone heard about BERT? Bidirectional embedding. Okay. This is some model which is now very basic for chat gpt. I mean, you can say very basic version of chat gpt. Okay, very basic version of chat gpt. जब मैंने एमटेक किया था, तो बर्ट वाज वेरी पॉपुलर एंड इट वाज हॉट नॉच। मतलब जिसको बर्ट आता है वो मतलब एक अच्छा मशीन लर्निंग इंजीनियर माना जाता था कि हाँ, बर्ट बर्ट पढ़ लिया, ठीक है। अब बर्ट को कोई भाव नहीं दे रहा है, ठीक है। मतलब मैंने जब 2019 में एमटेक किया था, तो आई रिमेम्बर मेरा अमेजोन इंटरव्यू में दे वर आस्किंग समथिंग अबाउट बर्ट एंड दीस थिंग्स, राइट। अब बर्ट शुड बी समथिंग दैट एवरीवन शुड नो, मतलब वो एमटेक में ही आ जाना चाहिए। मेरे टाइम पे एमटेक पास आउट करने के बाद मैंने बर्ट पढ़ा था। अब वो नाउ दे आर एक्सपेक्टिंग कि बर्ट तो एमटेक में आना चाहिए, है ना। तो अब क्योंकि उनको एमटेक, फॉर एग्जांपल दे आर एक्सपेक्टिंग कि बर्ट एमटेक फर्स्ट ईयर में आना चाहिए, क्योंकि एमटेक सेकंड ईयर में उनको और ज्यादा कॉम्प्लेक्स चीजें पढ़ानी है, राइट। सो बेसिकली द थिंग्स आर लाइक दिस। मतलब पहले बर्ट फॉर एग्जांपल पहले बर्ट एमटेक से भी बाहर था। ओके, मतलब एमटेक अगर यहाँ पे है, तो बर्ट आफ्टर एमटेक करते थे लोग। आफ्टर एमटेक लाइक लोग समझ रहे हैं, फॉर एग्जांपल आई एम जस्ट गिविंग यू द एग्जांपल। ओके, आफ्टर एमटेक लोग बर्ट समझ रहे हैं, क्योंकि उसके बाद कुछ है ही नहीं। अब यहाँ पे क्या हुआ कि और ज्यादा कॉम्प्लेक्स चीजें आ गई आफ्टर एमटेक, तो उन्होंने बर्ट को एमटेक में शिफ्ट कर दिया। फिर एमटेक में जो था उसको क्या किया, उसको बीटेक में शिफ्ट कर दिया, है ना, कि बीटेक से पहले आना चाहिए। Okay, so something like this. Are you getting my point? So why they have introduced gate DA? Because they want ki whenever you are taking admission into MTech, they do not have to teach the linear transformation. ओके, दे आर एक्सपेक्टिंग यू टू नो द लीनियर ट्रांसफॉर्मेशन सो दैट देयर वर्क इज इजी, क्योंकि उनके पास बहुत काम है अभी। पहले उनके पास इतना नहीं था, मतलब पहले उनके पास टाइम था कि वो लीनियर ट्रांसफॉर्मेशन और चेंज ऑफ बेसिस या फिर लीनियर अलजेब्रा में एसवीडी, सिंगुलर वैल्यूड डिकम्पोजिशन, ये सब पढ़ा दें, पहले उनके पास ये टाइम था। अब उनके पास टाइम नहीं बचेगा आफ्टर फ्यू इयर्स, मे बी आफ्टर 5 years दे वॉन्ट बी हैविंग टाइम टू टीच एसवीडी। सी, अभी वो पढ़ा रहे हैं, अभी भी लाइक इन द आईएससी, इन द आईआईटी बॉम्बे और इन दीज काइंड ऑफ कॉलेजेस, they will teach you SVD anyway. Like in MTech, they will teach you singular value decomposition. I think at least for 5 more years, they will teach you. Okay. For 5 more years, they will teach SVD, they will teach the basics. But I think after 5 years, they will be having so much things to teach that they will say that, okay, now it is no more, no more SVD. You are expected to know SVD before coming to MTech. It's just like that. Okay. Because field is evolving. Okay. Anyway, so just coming here. Okay. Now let's just see this. Which of the following transformation are linear? Can you tell me quickly? Is this linear? Just tell me y or n. Yes or no? The first one or linear or not? Yeah, first one is not a linear because of the constant, right? Okay. Tell me the second one. I mean, you can see the origin is not 0 0 is not mapping to 0 0 0, right? Tell me the second one. Sorry, it is comma. Okay, it is comma here. Okay, it is comma. So I think this is linear. Okay, sorry, it is not comma. I'm sorry about it. It is R2. It is R2. It is not comma. It is like this only. Anyway, it doesn't really matter. It is linear, right? Still, it is linear entries. So it is linear. What about this? Is this linear? Do you think the origin is mapping to origin? No, right? This is not linear because of the constant. Is this linear? Sin x, is this linear? Is this some c into x plus c2 into y or something like that? This is not also linear, right? This is not linear. So this is not linear, not okay. They are asking linear. So I think B is the only correct answer. Let's just see. Okay. So see here, B is the only correct answer, right? Don't worry about this matrix and all. We will talk about these things. But are you good with the basics? I mean, is the short trick working with everyone? Okay. That it is a linear function of the entries and constant term should not be there. Okay. And when I say linear function, it should be something like this: c1x plus c2y plus c3z. Okay. This is linear function of entries. Okay. Now let's just see this particular question. This is a true false question. Okay. Tell me this is true or false. What they're saying is that these vectors are linearly independent and the linear transformation, I mean, given is the okay, this one we have not studied yet. Sorry about it. We will okay. First, let me just teach you this one-to-one function and all, and then I will talk about it. Okay, just let me just skip this question for a moment. Okay. So let's now do this question. Tell me if it is a linear transformation or not. R2 to R2 and something like this. Tell me this is a linear. What do you think? This is this is not a linear transformation because of this multiplication. What about this? This is a linear transformation, right? This is no, this is yes. Okay. Not a linear transformation. This is a linear transformation. Okay. Don't worry about these matrices. I will come to that. But yeah, let's just see if you can identify if something is linear transformation or not. Let's just quickly do one or two more examples. Which of the following property of linear transformation does T satisfy? Tell me. Is it satisfying any of the property? See, it is not satisfying this definitely because C might be negative number, and if you multiply that later on, it will be the negative, right? So yeah, this should not satisfy this property. What about this property? See, interestingly, if you add them later on, this is very interesting. Do you know this x plus y, or maybe some any other number? Maybe you can take p plus q, okay, or maybe r plus s. This modulus, and do you know the relationship between these two quantities? Which one is greater or equal? Which one is greater? Yeah, this one, right? Do you know this property? See, here you are always adding, right? You are always adding R and S. But here it is a chance of adding, or maybe sometimes if S is negative or R is negative, you can subtract each other, right? You may end up subtract each other if one of them is negative or something like this, right? Yeah, this is also called triangular inequality. Okay, but anyway, the intuitively you can understand that here you're always adding, right? Always adding, irrespective of the value of R and S. I mean, whether it is positive or negative, you're always adding. This is absolute value addition. Okay, and here you are sometimes you may add, sometimes you may subtract, depending whether both are having same sign or different sign, right? Okay. So basically what I'm trying to say here is that if you first take the transformation, then you are doing something like this. I mean, you are taking the absolute values, and then you are adding. But if you're first adding, then you may end up subtracting, right? You may end up subtracting. So that's why this is also not satisfied. So none of them. You can say none of them, right? Okay. See here, that here, if you're taking the transformation, it will be, addition of the, I mean, if you're taking the transformation first, then it will be always the addition. It will be 1 and plus 1, right? But if you're first adding, it will be 0 0. See, they've also taken the example where the signs are different. Okay, the signs are different. Have you understood why this is not a property that it is satisfying? Because sometimes it may it may also subtract depending on the values of, or the signs of u and v, right? Should I explain it more, or it is okay? Let me know. I can explain if anyone having problem. You don't have to hesitate, you just let me know, I can explain. Okay, see what they are saying, that t of xy is okay. If you're getting confused by by flipping this, okay, by flipping this, let me just first take the simpler example by not flipping this. Okay, let's suppose this. Tell me tell me if you have two vectors. Okay, let me just take two vectors, -2 3 2 4, something like this, t of this. Then what is this t of this and t of this? You will say it is 2 plus 2 4, and 4 plus 3 7, isn't it? Tell me, is this okay to everyone? After transformation, it will be 2 3. After transformation, it will remain 2 4. So the addition will be, sorry, 4 and 7, right? The addition will be 4 and 7. Is this okay? Right? But if you first add, okay, which means if you first add -2 3 plus 2 and 4, then the problem is that, and then you take the transformation later on, the problem is that it is becoming 0. Then it will be 0 7. If you first add and then take the transformation later on, it will be 0 7, right? But if you first take the transformation, you are basically always adding. You are always adding, right? So that is why these two are not same. These two are not same. That's why it is not satisfying the property, right? Understood? Something like that. So basically, if you're first taking the transformation, then you're always adding. Here you are always adding, because the transformation is making the absolute value, the positive values. But if you're first adding, you may end up subtracting, right? You may end up subtracting. That is the problem. Similarly for this scalar quantity is that if you are multiplying by some c, okay, first you are multiplying the c and then you're taking the transformation. It is always, see, the transformation is always giving the absolute value. This is always the positive value, always positive value. Tell me, what is the sign of this if c is negative? Can this be negative value if c is negative? If the value of c is negative, then can this be negative, the whole thing? Yes, right? Whole thing can be negative, but it is always positive. It is always positive. But if c is negative, then it may be negative. That is the reason. That is the reason, right? That I will say that this property is also not satisfied. Okay. Okay. So now we will understand something like that, matrix of a linear transformation. Okay. Now let's just try to understand something like matrix of linear transformation. Before that, let's just do this question. Tell me, is this a linear transformation? Just check it. Okay. Just take your time and check it. A could be some random matrix, which is 2 by 3. Okay. Some random matrix, and tu is defined like this. So tell me if u is 3 by cross 3 cross 1 vector, then au is I mean, what is the dimension of au? It is 2 cross 3, 3 cross 1. What is the dimension of au? It is 2 cross 1, right? Okay. So which means it is from R3 to R2, right? It is from R3 to R2. Just check, just check. A could be any matrix. Just check whether it is a linear transformation or not. Okay. Just take your time, because it is very important and some basic building block of something. Okay. So just very important, where the linear transformation and the matrix multiplication will be mapping to each other. I mean, the relation between linear transformation and the matrix multiplication will get established after this particular example. But before I establish this relation, you just check it whether it is a linear transformation or not. Okay. Just take your time. Just take 1 minute and let me know. Okay. So I think most of you are saying it is a linear transformation. So Sonam has given a descriptive answer. This is very nice of her. So let me just paste that answer. So it is actually a linear transformation. Why it is a linear transformation? Because you just understand this. See, because you just check two properties, right? What are those two properties? Addition and scalar multiplication, right? Okay. So for example, this tu is nothing but au, right? So if you take two vectors, maybe let's suppose u and v, if you add them first and you take the transformation, what it will be? It will be transformation of anything is basically a into u plus v, right? It will be like this. Or you first take the transformation and then you add them later. Then what it will be? It will be au plus av, right? So you do this and you do this. Just check whether these two are same or not. I think these two are same, right? So that is why this particular property is satisfied. And also this very easy to check that you are also satisfying the second property, which is the multiplication property, right? So for example, this t of c of u, if you do this, it will be t of anything is a into c of u. Since c is a scalar, you can write it here, you can write it here, you can write it here, doesn't really matter. So which means it is same as c into au, right? Or you take the transformation first and then you multiply later on. It will be c into a and u, right? So yes, both of the properties are satisfied. So that is why it is a linear transformation, right? Okay. So which means that if you multiply by a matrix, then it is a linear transformation. So it is a very important thing to note that matrix multiplication is a linear transformation. Okay. Now, there is one other property which is also very interesting, that it is both ways, which means every linear transformation can be represented with a matrix also. So I will just show you how, but let me just first write it. Every linear transformation is just a matrix multiplication. Multiplication, which means it is both ways in the sense that if it is a matrix multiplication, then it is a linear transformation, right? Then it is a linear transformation. If it is a linear transformation, then also it is a matrix multiplication. So this thing I think we have done, right? If it is a matrix multiplication, then it is a linear transformation. Is this okay to everyone? We just proved it, right? We just proved it that if it is a matrix multiplication, right, then this kind of multiplication is actually a linear transformation. We have proved it. Tell me, is this okay? Is this okay to everyone? That if it is a matrix multiplication, then it is a linear transformation. But how the second thing is there, which means if it is a linear transformation, then there is a matrix associated with this, which means whatever examples we have talked till now, right? For example, maybe for example this B, right? See, it is a linear transformation or not? Tell me. We have seen that this is a linear transformation, right? Since it is a linear transformation, I'm telling you that there will be a matrix multiplication associated with it. Okay, what do I mean by that? And these things I will just tell you. But for now, I'm just telling you that for every linear transformation, there is a matrix. For example, for this particular linear transformation, this is a matrix. Okay, like that. I mean, I will tell you that how to calculate that matrix. But yeah, at least, are you convinced with this part that if it is a linear transformation, then it is a sorry, if it is a matrix multiplication, then it is a linear transformation. Are you convinced with this tick part, the first part? Yes, right. Okay. What about the second part? Let's just see the second part. If it is a linear transformation, then how does a matrix multiplication? We will see this, right? So the matrix of linear transformation, which means for every linear transformation, there is a matrix multiplication. But what do I mean by that and how to calculate that matrix? Let's just see. Okay. So for example, let's just find the matrix corresponding to this linear transformation. For example, let's suppose they give you some linear transformation, okay? And then they ask that, can you tell me the matrix associated with this linear transformation? So which means they are saying that suppose this t of x by is nothing but x plus y and x minus y. Tell me this is a linear transformation or not? First tell me this is a linear transformation or not? This is a linear transformation, right? I mean, it is AG to C. So this is a linear transformation, right? Now, I want to check whether for this linear transformation, I want to check what is the matrix for this linear transformation, okay? Which means, what do I mean by that? Let me just tell you. What do I mean by that? That that if you have this t of xy, which is giving you something like this, right? Like this, which is t of xy is x plus y, for example, and x minus y, okay? This is some linear transformation. Now, I want a matrix associated with that. What do I mean by that? It means that t of xy should be equal to some matrix A of, this t of basically xy should be some matrix A into xy, such that you finally get x plus y and x minus y. Okay, which means that if you are calculating t of xy, it is actually x plus y and x minus y. Either you calculate like this, or maybe you can multiply this xy a matrix, and it will also give you the same thing. Okay, and we want to find out this matrix. What is this matrix? We want to find out this matrix. Okay, so what I'm saying here is that if you do t of any xy, okay, t of xy, then tell me what it is giving you: x plus y, x plus y, and x minus y. Okay, I want to find a matrix such that instead of doing this transformation, I multiply a matrix with the vector xy and I get the same thing. I want to get this matrix A. Okay, how to get it? Can you decompose this? Do you know how to decompose? Can you tell me the decomposition? Something into x plus something into y. What is this decomposition? If you put x equal to 1 and y equal to 0, I think 1, 1, and x equal to 0 and y equal to 1, 1 minus 1, right? Can you do this decomposition? Tell me. Is this okay from here to here, this decomposition? Let me know anyone who finds difficulty in decomposition. Okay, I think most of you can do this, right? Okay. Now, given this decomposition, is this okay to fill this matrix A? What should be the matrix A? I think it is very easy, right? What is this matrix A? You can say this matrix A should be the same thing, right? 1, 1, 1 minus 1, right? Okay, great. So many of you has already given the correct answer, right? 1, 1 and 1 minus 1. Let me just write it here also. Many of you have already given the correct answer before I told the decomposition, right? Okay. So I hope you people are getting what I'm trying to say, right? So I'm saying here is that there is a linear transformation, and I want to get a matrix such that it performs the same task. Okay. And what is this matrix? 1, 1 and 1 minus 1. Right? Great. So see here that what I'm saying is that there is a linear transformation from R2 to R2 defined as like this. Suppose A is a corresponding matrix, then we must have okay something like this. Then what is the value of A1 and A2? I think using the decomposition you can tell me. Okay, that can be easily decomposed, right? Something into X and something into Y, and from here we can find out the value of A1 and A2. Okay. Okay. Great. Now, let's just take the same transformation, which is t of xy is x plus y and x minus y. Tell me, what is the transformation of the basis vector? What is the transformation of basis vector? Let's suppose 1, 0. And similarly, what is the transformation of basis vector that is 0, 1? What are these transformations? 0, 1, 0 will get you, I think 1, 0 itself, I think, right? Okay. And 0, 1 will get you 1, 0 minus 1, 1 minus 1, right? Sorry, 1, 0 will get you 1, 1. So 1, 0 will get you 1, 1, and 0, 1 will get you this. Is this fine to everyone? I'm just finding out the transformation of the basis vectors, right? Okay. Okay. Now, the matrix that we have found, okay, the matrix that we have found from the previous example was something like this. See, the matrix we have found was 1, 1 and 1 minus 1, right? This is same as this one is same as the matrix that we have found. One is same as this particular transformation, and one minus one is also same as this particular transformation. Which means, okay, I will tell you. I will also prove it, but for now, let me just write it. That which means it seems like the matrix. If you want to find out the matrix, then the shorthand notation is that you just find out the transformation of the first basis vector, and the transformation of the second basis vector, and you write them in the matrix. It will be your matrix, isn't it? I will prove it. I will tell you intuitively also. But at least with this example, is this okay? That you find out the transformation of the first basis, you write it. It is there. You write the transformation of the second basis, and whenever you are forming the matrix, you are getting the same matrix that you have calculated earlier, right? Okay. Okay. So what I'm trying to say, that for any, okay, in general, for any linear transformation, if you want to find out the matrix for any linear transformation, let's suppose T. If you want to find out the matrix, then what is that matrix? Is T of E1 is the first basis vector, E2 is the second basis vector. And if there are multiple basis vector, you can write them. Is this okay? Okay. So let me tell you what do I mean by that. See, let's just see with this example. Let's suppose you are taking the transformation of any random vector xyz. Then can you write the xyz like this? Is this okay to you guys? Can you write xyz like this? Yes, right? I mean, x into the first basis vector, y into the second basis vector, and so on, right? You can definitely write xyz like this. Okay. Now, now, can you uh, can you just apply the property of linear transformation, and can you just say that this is same as this, which means you are writing like this, and then this is x into, okay, just this is even, but you can take this x outside also because it is just a constant. Okay, this is a property of linear transformation, right? Now, you can always write this. I mean, this particular formulation you can always write like this, which is a matrix into a vector, right? You can always write like this also, which is, I mean, x into some vector plus y into some vector plus z into some vector. We are very much habitual of writing like this, right? This particular c into b1, c1 into b1, c2 into b2. We are very much habitual of writing like this, right? Which is same as a into some vector x. So we started with t of some vector and transformation of some vector, and then we got to know that here, if you want to represent that a into some vector, which is, I mean, you can represent an a same as the transformation of the basis vectors. Okay, why this work? Let me just tell you. Let's just take some example. Okay, and let me just tell you that why this work. Let's suppose the transformation. Okay, let's just take the earlier example itself, which is x plus y and x minus y. ठीक है? Let's take some vector xy, which is 3 2. Okay, tell me what is the transformation of 3 2? It is 5 and 1, right? 5 and 1. Now you want a matrix such that if you multiply 3 2 with that, it gives you 5 and 1, right? I mean, that's what we are looking for. So so you want a matrix A such that if you multiply by 3 2, it gives you 5 and 1. I mean, this is our aim, right? This is what we are looking for. Okay. The A. Okay, we are looking for the A. Now, now see, let me just go to the next page. Now see here, we want A into 3, 2, such that it give you 5 and 1, right? Now what will I do? What will I do? I will write this 3, 2 as something like this. A into, I will write this 3, 2 like this. 3 into the first basis vector plus 2 into the second basis vector. Okay, cool. Now, which is same as 3 into A into the first basis vector plus 2 into A of second basis vector. Let's suppose A is nothing but A1, A2, right? Now you tell me what it will be. 3 into A1 plus 2 into A2, right? Is this fine to everyone? That what I'm trying to say here is that you multiply the matrix this A with 3 2, you got 3 into A1. I mean that's easy to check. The 3 into the first vector A1 and 2 into the second vector A2. Even if you don't want to write this in between, then also you will be getting like this, right? Okay. Now let's just do one thing. What happens if we apply the transformation here? See, if we apply the transformation, then tell me, is this okay to everyone? That transformation of 3 2 is nothing but I mean you can rewrite like this, and using the transformation property you can like write like this. I mean this is distributive over the plus, and then you can take this 3 outside, right? Using the transformation property I can go from here to here. Okay, so using the transformation I'm getting something like this. Is this okay? And if you multiply this 3 2 by let's suppose the matrix A, then what are you getting? If you multiply this 3 2 by the matrix A, then what are you getting? A is nothing but A1, A2. Okay. Then also you are getting 3 into A1 plus 2 into A2. So basically, if you multiply by the matrix, then you are getting 3 into A1 plus 2 into A2. Let me know if that is fine. Is this line fine to everyone? If you multiply a vector with the matrix, then I think this is something we have been doing since a long time, right? Okay. If you apply the transformation, then I have taken the help of basis vectors. Okay, I mean for the matrix multiplication actually you can just forget about it. We do not need the basis vector introduction here. But yeah, for the transformation, let's suppose I'm writing in terms of the basis vector. Okay, for example, what I'm trying to say here is that, okay, whenever, let's suppose I want this t of 3 2, right? I want this t of 3 2. So I written in terms of the basis vector first, and then I'm taking the transformation. I mean I'm not taking, let's suppose, the transformation directly. I'm taking the transformation after the basis vectors, after writing in terms of the basis vector. Okay, so I'm getting something like this. And if you're directly multiplying by the matrix, you are getting something like this. Can you compare this these two formulation? Can you tell me the value of a1? Isn't it same as this? Isn't it this a1? Isn't it this a2? Tell me. Can you compare these two? And can you tell me what is this A1 and A2? So basically from here you can easily see that the A1 and A2, okay, are same as the transformation of the basis vectors only. Okay. So A1 and A2 are same as transformation of the basis vectors. And why that is so, that also we will talk about. But for example, I mean, using this, is this fine to everyone? That if you just multiply by the matrix, then you are getting something like this. If you take the transformation, then you are getting something like this. Your job is to just identify, is this A1 or not, is this A2 or not. This is right, this is. So these are A1 and A2 for sure. Now you can definitely, I mean, if you want, you can definitely do one thing. You can definitely generalize this in the sense, there is no need of 3 and 2. Okay, there is no need of 3 and 2. You can write in terms of x and y also. So for example, I mean, the 3 2 was just an example here, but you can write in terms of x y also. See, what I'm trying to say here is that you can write here x, here y, here x, here y. This is x, this is y. I mean, in general, I'm just telling you that you have any transformation, you write like this. I mean, if before taking the transformation, you just decompose in terms of the basis vectors, right? And then you just compare these two. You just compare these two. You will get your A1 and A2. What is the A1? If you compare these two, this A1 and this thing is same, right? This is same. Similarly, this A2 and this thing is same, isn't it? If this transformation, I'm assuming that the transformation is equal to, let's suppose, this matrix A, then what does this matrix say? A is nothing but transformation of the first basis vector and the transformation of the second basis vector. ठीक है? Okay, is this understood, that what I'm trying to say here? See, the matrix multiplication, at least this part is okay, right? I mean, if you're doing the matrix multiplication, you will be getting something like this. Now it is just that before taking the transformation, I'm just writing in the terms of basis vector before taking the transformation. Okay, I'm just trying to write in terms of basis vectors. And now I got to know that, oh, that's really nice to see that these basis vectors that I, okay, after writing the basis vectors, the vectors that I'm getting, 3 into some vector plus 2 into some vector, are nothing but a matrix, the matrix columns only. Okay, it's very straightforward to see now. Okay, so maybe little bit you have got, but let's just do more examples, and let's just try to understand this more. Okay, so see here, in general the matrix A is nothing but t of e1, t of t2, like this. Okay, let's just see example, and after that it will be more clear. Okay, the matrix associated with the linear transformation is called standard matrix. Okay, I mean, the A that we are talking about, it is also called as standard matrix. Let's just see this question, what they're trying to say. Suppose the linear transformation is something like this. Okay, x into this and y into this. Can you tell me the matrix here? What is the matrix A into x, such that it works. Okay, A into v. Okay, A into v, such that it works exactly like this. Okay, exactly like the linear transformation, which is x into 103 and y into 2 4 minus 1. What is that matrix A? V is nothing but xy. Okay, tell me, what is that matrix A such that this property is satisfied? Very easy to see, right? So this is 103 and 2 4 minus 1, right? So A is very straightforward to see, that A is nothing but. ठीक है? Okay. Let's just see this. Find the standard matrix for this linear transformation such that they have given the transformation only for the basis vectors. Can you tell me what is that matrix say? This is, yes. So that is correct. Diksha has given the correct answer. Okay, let me write her answer here also. This, which is 210, right? Yeah, 210 00011, like this, right? Okay. So it is 210 011 221. Okay. Okay. So Bachu Paul is saying that this T of E3 is nothing but E1 plus E2. Okay. Yeah, then these are not basis vectors actually. Okay, maybe there are some misprinting. I mean, you can just take it as two or something. Okay, I mean one of the value you can take something else. Okay, maybe you can take just two or something. Okay, doesn't really matter. Okay, now now just see one thing here is that let's suppose there's a box. Okay, let's suppose there's a box. I call this box as a linear transformation. Okay, I call this box as a linear transformation. Then let's suppose this v1 vector is going here, and then what is coming out? T of v1. Okay, and then maybe v2 vector is going here, and what is coming out? T of v2. Let's suppose I do not know the closed form. I mean, I do not know that for I mean closed form in the sense that, okay, what is the formulation of this? For example, the formula could of the transformation could be like this, or could be like something else also, right? Formula of the transformation could be like something else also. Okay. So basically, let's suppose I do not know that what is the closed form. Maybe it is x plus y, x minus y, okay, x, something like that. Okay. Maybe something like that. Let's suppose I do not know. Now, if someone asks me that how many, if you do not know the closed form, then how many vectors do you really need to know? I mean, which means I want to define this linear transformation completely. Okay, I want to define this linear transformation in its entirety. And it means that there is no ambiguity here. So if I tell you, let's suppose there are in my input, there are infinitely many vectors. Okay, infinitely many vectors. So is it feasible to tell you, if you do not know the closed form, is it feasible to tell you the transformation for infinitely many vectors from here to here? If you do not know the closed form, is it feasible to tell, okay, 1 2 जो है वो let's suppose 3 4 में जाएगा, है ना, 2 1 जो है let's suppose इसमें इसमें आएगा, something like that. Is it feasible to tell for every 1 2 2 1, or whatever is this? No, right? I don't think for infinitely many vectors you can list down them, right? Suppose you do not know the closed form. Okay, you do not know the formula. Then what is the best way? Can you tell me the minimum number of vectors? Okay, so that I do not need to know the closed form, and I still know the linear transformation. What are those minimum number of vectors? Those are the basis vectors. Which means suppose I do not know what is the closed form, but still I know one thing. Let's suppose still I know that, suppose I just know these things, that E1 goes to T1, E2 goes to TE2, and let's suppose there are three basis vectors, and E3 goes to TE3. Now, can you tell me the linear transformation in its entirety? What is this linear transformation? Yes, you can tell that, okay, linear transformation matrix is this. Which means if you know the linear transformation of the basis vectors, don't you know the linear transformation of all the vectors? Now you give me any vector, I will tell you the linear transformation of that vector. You give me any vector v. What is the linear transformation of that vector v? This is AB, right? This is AB. So So if you know the linear transformation of the basis vectors, then you know the linear transformation in its entirety, right? So which means now for any vector v, we have linear transformation. And what is that linear transformation? AB, right? But if you give me any random linear transformation, any random five vectors linear transformation, do you have the complete linear transformation with you? Tell me. No, right? But if you have the basis vectors linear transformation, then you have the complete linear transformation with you, because now you can find the matrix associated with the linear transformation, and then you can find the linear transformation for any other vector, right? So I can say that if we have the linear transformation of the basis vectors, then we have the complete linear transformation, right? If we have linear transformation of basis vectors, then I can say then we have linear transformation of all vectors, right? Is this understood to you guys? Let me know. If you have linear transformation of basis vector, don't you have the complete linear transformation? How it will be given? The complete linear transformation will be given like this, where T1, T2, and T3 are the linear transformation of basis vectors, right? Okay, let's do more example. Probably you will get to understand more. Let's see this question. Let T be the associated matrix. Let T be the associated matrix transformation. ATX equal to AX. Choose the vector V below that satisfies TV equal to even. Okay, even by default is 1. Which vector is giving you 1, 0? Can you just do this? Which means T of B means you can either multiply by the a 2 of 1, 2 1 1 1 into some xy should give you 1, 0. What is this xy? Can you solve for the xy? I think you can do it, right? So what is the answer you are getting? Maybe you can cross verify. I think one of this minus one of this. I think this, right? Is this the answer? Yeah. So I think xy you are getting like this. Can you tell me how many such xy exist? I mean, how many are the solution for this xy? How many such xy exist? Can you tell me? Is this having infinite solutions or like this? Tell me that how many pivot elements are here? I think if you subtract two of this, then I think both are the pivot, right? You subtract two of this. I mean, you can easily see that both columns are linearly independent, right? Since both columns are linearly independent, then there is a unique solution, right? Since both columns are linearly independent, hence you can say unique solution. Okay. So what is the answer of the part B? Exactly one solution, right? Okay. Let's do this question. Maybe just a second. Let's do this question. Tell me what is the answer you will be getting here. Okay, do you understand range and all? Or maybe I can first introduce on to one to range and these things. I mean the function definition of function terminology. What is on to function? What is this function? And then maybe after that I can do this question. Okay, just for now, let me just hold this question. I can tell you the function terminology, and then I can do that particular question. Okay. For now, let's just solve more question. Yeah. So for now, let's just solve more questions related to this these definitions. Okay. Let's just see this. Find the standard matrix A for T. In other words, find the matrix A so that Tx equal to Ax. Can you do this as an homework? How you will be doing it? What is A? What is A? It will be nothing but T of 100, T of 010, T of 001, right? Like this. So you have your T with you. I think you can find out 100 and these things, right? Okay. What is T of 100? It is 0, uh, 2 minus, it is 2 basically, and it is 3. Oh, sorry, it is 0, and then it is x1. X1 is 1. 0 to 0 1. 0 to 0 1. Either A is answer or D is answer, right? Okay. Now, I think I can calculate T of 001. So T of 001. 0 x3 ही केवल 1 है ना. 0 minus 3 and 0. 0 0 minus 3 and 0. 0 0 minus 3 and 0. I think A is the correct answer, right? ठीक है. So this is coming out to be 0 0 minus 3 and 0. Is this okay to everyone? How we calculated? Okay. Okay. So I hope that was okay to everyone. So the answer is this one, right? Now let's just do this. So actually, I was thinking that we can directly introduce with the with the questions. Is this okay? I can directly introduce with the question. What is domain, codomain, and these things for any function? Or maybe if you want, I can just first introduce. Or maybe okay, let me just first introduce in the next session. I will introduce, and then we can talk about these kind of problems. Yeah. So let's just do this. Let's just do this question. This is very interesting. Let's just solve this question. What they're trying to say is that S and T, they have given two linear transformation. Okay. Associated with S is associated with B, and I mean B is basically for S and T is for A. Now they are saying, let's just define another linear transformation T such that it is T of Sx. Then what is the matrix corresponding to this U? See, what is the first transformation that you are doing? First is S, right? First is S. So for any X, first is S. So what you will do? You will multiply to transform into S. Transform using S, you will multiply by A or B. Tell me. For the S, you are multiplying by B, right? So first you are doing S, so you will be multiplying by B, and the whole thing you are doing with T. Then you will be multiplying by, for the transformation using T, you will be multiplying by A, right? So this is nothing but the transformation using U. So basically, the matrix they are asking is the standard matrix corresponding to U is nothing but AB. Okay, so answer is AB. You can multiply A and B, you can get your answer. I mean, this is a composite function. I hope you understood what I'm trying to say. First, you are taking the transformation using S, and then you assume this is Y. Okay, this is Y. Then you're taking the transformation using T, right? I mean, this is just a quick summary I want to give you. But for now, I want you to analyze this question. If there is any doubt, you can just let me know later on. I'm giving you as a homework. Just analyze what I just said, right? Okay, just analysis is an homework, and if you have any doubt later on, you can just ask me. So what I'm trying to say is that you are first doing the transformation using S, and then you are doing the transformation using T, right? That is why this is the answer. Just try to do by your own also. Okay. Cool. So all of these questions we can do later on. Yeah. This is very tricky question. Okay. For now it is tricky. Just try this question also. Okay. Very tricky. Answer on the next page. We will do this tomorrow for sure. But try this question as a homework. Okay. We will also do this. Right. The answer is on the next page, but you just try this. Okay. This is very nice. Not tricky. I will say it is nice question. Easy question only, but it is nice. Okay. It is not tricky. I will say it is just nice question. Okay. So let's just do one thing. Tomorrow I will finish this linear transformation with on to one to whatever the function definition and these things. Okay. Tomorrow I will finish this linear transformation and then we will start a new topic. A new topic will be. Can anyone guess the new topic? It will be diagonalization. Okay. It will be diagonalization. So we will, once we finish all of these basics, then we will be starting SVD and these things, eigenvalue decomposition. If we finish, and then we will be starting the SVD. It is very interesting topic. SVD is very interesting topic. And after that, there will be few minor topics will be remaining, like projection of a matrix and projection matrix and these things, right? So we will cover those also. Okay, cool. And now, today I will prepare the cues, and tomorrow morning you will be getting the cues. Okay, cool. So thank you everyone. Take care. Bye bye.